All right. So let's talk about another family of integrals that we'll run into. And basically, they look like these, right? So they look pretty complicated here. And so, uh, how would we integrate something like this? None of our tools let us do this. Now, first of all, be aware that in these formulas, a is typically a constant, okay, and u is our variable. Sometimes it'll just appear as an x. But what you see is these integrals actually have antiderivatives, or the integral of these kinds of things turns out to be uh, these inverse trig functions. All right, and we know that because when we were differentiating these kinds of things, we got these kinds of things. All right, so we're just working in reverse, and so these are integrals that you'll add to your integral table. Integrals that you just have to recognize the pattern and then uh, see how to integrate them. So um, let's look at an example here and see how it works. So let's integrate. Um, let's just go from negative 1/2 to 1/2. Oops, let's try that. Dx over square root of 1 minus x squared. All right. And so when you come across one of these things, you have to recognize the pattern, and if you have to see which one of these patterns it fits, and it doesn't take us too long to realize, hey, this fits this pattern. What you're looking for is, of course, a square root of something minus your variable squared. Here we're lacking the square root. Here um, things are kind of swapped in order, but you also have the variable floating outside here. All right. So this fits that very first pattern, and so we say, okay, well, we know what the antiderivative of this is going to be. It's going to be the inverse sine of x over a. In this case, a is 1, right? So x over a, so just x. And then, of course, since we have limits, we evaluated the limits. And so if we go ahead and plug those in to the inverse sine, we're going to end up taking the inverse sine of 1/2, which is pi sixths, minus the inverse sine of negative 1/2, which is negative, or sorry, it is 11 pi sixths, or no, let's take that back. It's negative pi sixths, so minus pi sixths. So we end up with 2 pi sixths, or pi thirds. And so we can see that we just evaluate those. Once we have the pattern down, then we've recognized the pattern, then we can just plug things into the pattern. Let's look at another one. So let's do the integral of dx over 25 plus 16x squared, right? And so we want to see which pattern that fits. Again, it looks like it's fitting our first this one's fitting our second one, the inverse tangent, right? The thing to notice in here real quickly is it will fit the pattern if we let u equal 5, right? That gives us sorry, not u equal 5. Let's try that again. If we let a equal 5, then of course 5 squared is 25, and then u itself is going to be 4x, right? Because when you square u, you get 16x squared. So once we understand what the values a and u take on, we can just plug that into our formula. So this is going to be 1 over a times the inverse tangent of u over a plus c, right? So all we have to do is make sure we identify the correct pieces and then put them into the formula that we get from the integration table. And that's pretty handy to be able to do, all right? So now, once you have these things, you can start working on more complicated kinds of integrals when you couple this with, say, substitution. All right, so let's take a look at this integral right here. It doesn't take us too long to realize that this thing is way more complicated than our little formulas allow for, right, or take into account for. It looks on the outside like it might involve, might be the inverse secant one, integral, because we've got a variable outside the square root, and then inside the square root you have your variable minus something. Because remember, the inverse sign is the something minus the variable. So this one looks like it's headed towards the inverse secant. Now, it's way more complicated than that previous example to just simply call A something and U something. We're going to want to see if we can't make some substitutions here and see if some things will simplify. All right. So the first thing we might try is something like this. We might say, okay, let's let U equal t squared. The reason we do that is because if we did that, you'll see that this becomes just u, and this becomes, or sorry, that first one becomes u squared, and then this becomes u squared, and this will become a u, right? And so maybe some things will happen that will let us fit this into the inverse secant derivative. Now, of course, du dt is 2t, so dt equals du over 2t. Okay, so when we make those substitutions, it's going to look like this. We're just going to substitute in for what we can at the moment. So we've got our t, we've got inverse secant of u, right? So that kind of simplifies that, over u square root of u squared minus 1, right? Because u squared is t to the fourth. And then dt becomes a du over 2t. And this is another reason we kind of like this substitution, because it looks like we should be able to just cancel those things out. So we're left with, let's rewrite it, 1/2 the integral of, I'm going to write it like this, du over u square root of u squared minus 1. I'm actually going to pull the secant, inverse secant, off the top right there. Okay? All right, so there is our, there is the simplified version after we've done the substitution. Okay, so we're still way more complicated. Well, not way more, we're a little simpler. But the problem is we've got this secant that's part of the integral, right? If we didn't have this inverse secant, we'd just be good to go, and that would be the inverse secant of u, right? Now remember, there's a relation. So this doesn't fit our formulas yet, but remember, we hope we can do a substitution here. And remember, the idea with the substitution is you let u equal something, and you hope that the derivative of that something is part of the function. And I just look at this and I notice, hey, the derivative of inverse secant is this guy right here, right? So that kind of tells me that I can try this substitution. Let's let v equal inverse secant of u. That means dv du is equal to this guy, 1 over u square root of u squared minus 1. And so that means that du is equal to u square root of u squared minus 1 dv, right? Now watch what happens when I substitute everything in that I can, again, into here. I still have the 1/2 out in front. I've got, let's put the, we'll move the du out. So I still have this piece still there. Secant, inverse secant of u is v, and then du is u square root of u squared minus 1 dv. And look what happens. Bam, all of that kills all of that, and we're left with just the integral of v dv, which we can just now integrate using basic power rules. it'll be v squared over 2 plus c. So that's, of course, 1/4 v squared plus c. But now we got to turn it back to u's. So that's 1/4. V was inverse secant of u squared plus c, right? We've changed it back to u's. Now we need to change it back to t's, okay? And u is t squared, so squeeze that in here. 1/4 inverse secant of t squared, all of that squared plus c. And there it is. There is our integral of that. So we used a combination of our formulas with the u substitution that we're already familiar with.